All right, so page 33, normal approximation to the binomial. We'll get right into an example here, but the idea is that we are using our knowledge of normal distributions to evaluate binomial probability situations. All right, so little scenario, the owner of a new apartment building must install 25 water heaters. From past experience in other apartment buildings, she knows that Quick Hot is a good brand. A Quick Hot heater is guaranteed for 5 years only, but from her past experience, she knows that the probability will last 10 years is about 0.25. All right, and so this, like I'm sure we're not overly interested in water heaters, but any situation in which there would be a warranty involved. Like when you buy tires for a car, it's like you have a warranty up to 50,000 miles. The new car warranties now, I want to say they're in the neighborhood of 3 years, 36,000 miles. So it's like, that the newer the item is, the more likely it is that it'll function as intended. But as it gets older, things are going to break down. So it's a question of, will that breakdown be covered under warranty, or will the item last longer than the warranty, in which case you'd be out of pocket for your expenses. Right, so that's kind of what this is getting at. It's loosely related, not 100%, but that's the spirit of the question. Right, so we want to use a binomial method, and so by saying that it's a binomial method, we don't have to worry about verifying the four conditions: fixed number of trials, fixed probability, independent events, two outcomes. They're basically saying, regardless of whether those conditions are satisfied, you're supposed to use the binomial probability method. All right, so we want to know the probability of 8 or more of the 25 water heaters will last at least 10 years. So 8 or more, you got 25 water heaters, maybe none of them last 10 years, maybe only one, only two, only three, 8, 10, all 25. That's the array of possibilities. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 25. What they're saying is that we're looking for the probability of this set. Right? Now, if I use my binom CDF method in my calculator, so toolbox probability distributions, binomial noise. So our binom CDF M and P returns the probability that X is less than or equal to M. So whatever your M value is, that's going to be the maximum in our probability. If I want the probability of 8 or more, what I could do is figure out the probability of 7 or less. So I would do probability X is less than or equal to 7 and subtract that result from 1. All right, so it's in the complement rule stratosphere, I guess. It's basically saying, figure out the probability of the stuff that you don't want, subtract it from 1, and you'll get the probability of the stuff that you do want. So 1 minus binom CDF, 7, the number of trials 25, probability of success 0.25. That gets popped into your calculator. And we get about 0.273. Now, assuming that there's a fixed number of trials, and there's 25 water heaters, there's no reason to think that number is going to change. Fixed probability, 0.25. Kind of taking that on faith, because whenever you're dealing with real world context, you could say, the probability of success is 0.25, but then that could change over time. But we'll assume that is static. Independent events, it's either going to last for 10 years or not. Two outcomes, two outcomes that it's going to last 10 years or not. Independent events, that's one that's kind of tricky, and you'd have to assume it. Again, they told us it's binomial, so we don't really have to worry about that. But if one boiler or water heater breaks down let's say after 2 years, that might not be independent from all the other water heaters because maybe they were produced in the same batch at whatever factory, right? Or maybe they all have the same defective part. So there would be a dependent relationship there, but we'll make the assumption that it's independent, right? If all of those conditions are in place, then we can be satisfied that this is the correct probability. The correct probability that 8 or more of the water heaters are going to last 10 years. All right. Now, I don't know that that's an impressive number. They're only supposed to last 5 years. And by the way, that's not a thing. I mean, if a water heater only lasts 5 years, then you got not a good water heater. All right. So they should last 10 years or more. But, less than half lasting 10 years, it doesn't seem like a good number, but that's the way the question is phrased. So now we're going to do it with a normal curve to determine the probability that 8 or more of the water heaters will last at least 10 years. And when we do something with a normal curve, we need to know 2 pieces of information: the population mean and the population standard deviation. All right. Because we're saying that this is binomial, we could use mu equals NP and sigma is equal to square root of NPQ. The Q being 1 minus P, right? P is probability of success, Q is probability of failure. Right, so 25 objects, probability of success 0.25. That'll give us 6.25. 25, 0.25, 0.75, all under a radical. I believe that's 2.165, but we'll see. Just going by memory there. Yeah, 2.165. So we have our mean and our standard deviation. We would use a norm CDF range or norm CDF, depending on how you want to approach it. So what I'm asked for here is the probability that X is greater than or equal to 8. So I need to know the corresponding Z-score. Z is equal to X minus mu over sigma. So 8 minus 6.25 over 2.165. So I'll crunch those numbers. And just as a quick aside, we're not doing anything different so far. Everything that we've done in this problem has been stuff that we've already learned. All right? It's just a question of how this answer is going to relate to our answer to number 1. All right? It's going to be in the same neighborhood, but is it close enough to what it should be? That's really where we're at. So 0.808 is my Z-score. So I'm looking for the probability that Z is greater than or equal to 0.808. All right, so I'll run that through my norm CDF. I'll do a quick diagram. It's really not the purpose of this question to go full-blown AP-FRQ, but you should have the diagram there. But I'll just give you the bare bones of it. Here's 0. We're probably looking at something like this. All right, so this would be a norm CDF. I'm going to use range. The only time I really use norm CDF is if it's a less than or equal situation. Everything else I use norm CDF range. Even though I could do 1 minus norm CDF, I just never end up doing it that way. So 0.808, something big, 0, 1. So probability distribution is normal, norm CDF range, 0.808, bless you, something big, 0, 1 for the mean and standard deviation. All right, now you might say, well, didn't we say the mean was 6.25 and the standard deviation 2.165? Once we standardize it, once we make a Z-score, we've brought it into the universe where the mean and standard deviation are 0 and 1 respectively. All right, so this is going to be about 0.2095, so 0.210. All right, so it's off by 0.063. Right, so it's in the same neighborhood. It's in the 20% area, 20 to 30%. But can we get a better number? That's really what this is all about. Right, and we can by using something called continuity correction. All right. So in number 3, they're asking us to do essentially the same thing, but we're going to correct for continuity. And what that means is kind of beefy term, but when you're working with a discrete random variable, we really shouldn't be using normal distributions because normal distributions correspond to continuous data sets. All right, so remember, discrete data points are countable. All right, number of people in a room, number of rooms in a building. All right, the continuous values, you require a measuring device to determine its value. Right, so height, weight, distance, temperature, things like that. Like a lot of people look at it like you can't have decimals with discrete. Right, discrete values, no decimal values. It's all whole number values. Right, continuous values you could have decimals, but there's gray area there, so I try to stay away from that. But it's a decent rule of thumb. All right, so what I'm going to do here is I'm just going to use the more streamlined version of it. So we're looking for the probability that x is greater than or equal to 7.5 rather than 8. Right, instead of doing all this work again, I'm just going to jump to the norm CDF range. 7.5 on up to something big with the mean. Now, I didn't standardize. I didn't make a z-score out of this. So I'm going to go with the original mean of 6.25 and the original standard deviation of 2.165. All right, could have done that with the previous one, but I always have it in mind that it could be a free response question, in which case you can't skip all this stuff. All right, all of this stuff here. That would need to be included. But if I wanted to, I could do norm CDF range with the 8, something big, put in my 6.25 and my 2.165. It gives us the same decimal, or close enough, right? But now I'm doing it with 7.5 instead of 8. Oops. So we're looking at about 0.282. And, again, you go up to something big. If you're not sure that you landed on the right decimal, go bigger and see if there's any change in the decimal output. All right, there isn't, so we're good. All right, so this is off by 0.00, it looks like 009. All right, so less than 1%. So number 3 gives a more accurate approximation, right? There's only about 1% deviation from the correct probability. All right, so the natural question is, okay, that gave us the better answer. How would I know to do that? Right. So there's more advanced math that goes into this, but generally it's been determined that if you give yourself a half a unit of wiggle room in either direction, that will close the gap sufficiently between discrete random variables and continuous random variables. Right, so there's more to it than that. It's like, where did we come up with that 0.5? It certainly wasn't trial and error. It's based in calculus, integral calculus, so it's like second semester college calculus. So, we're not all there. So for now, we just kind of take it on faith that, okay, that 0.5 rule will work, right? And a lot of the times that's what we do. It's like, how did you determine that value? Who cares? It works, right? I don't love it, but, for an introductory stat class, that's kind of where we're at. Right. There is a little bit of a justification on the next page of where that 0.5 comes from, right? So that certainly not as visible on yours as it is here, but that that red one here, that corresponds with the correct probabilities. So that's no deviation. It's not gonna give me a normal curve. Yeah, I didn't think it would. All right, but this red one. here corresponds with the correct distribution. The one that gets us that close, but not too close, approximation is the one corresponding with 0.5. All right, so I mean it's not really an explanation. There is an explanation here, but it's basically what I'm saying is that the one that works the best is 0.5. Now the question is, do I add 0.5? Do I subtract 0.5? That goes back to this table here. You can just kind of follow that if you want, but my recommendation is to kind of consider what addition or subtraction of 0.5 is going to capture the number that you want to be captured in the appropriate interval. All right, so if I'm going, like, for example, I'll just go back to the 8 or above. So let's say, I'm going to thinner marker. Yeah, this is good. So if I'm looking for the probability that x is greater than or equal to 8, all right, and I want to use with continuity correction, which is abbreviated CC, which hopefully makes sense. All right, so I'm just going to do that number line thing again. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on, up to 25. All right. Now, if I want 8 or more, I'm looking at this interval here. And just based on the way I drew the box, it kind of leads you to the 7.5. All right. So this value, this cutoff here, 7.5, for continuity correction, that's going to get the job done. Had I gone with 8.5, I'll just show you real quick. You don't have to write this. I'll just move this for a sec. Let's say I did my cutoff at 8.5. So instead of subtracting 0.5, I added 0.5. That would put me here, and I wouldn't get my 8. All right, if I want less than or equal to 8, 8 should be in the box that I draw. All right, if this said probability that x was greater than 8, then that would work. All right, I'd have 8.5 as my cutoff. The first value beyond 8.5 would be 9 all the way up to 25. But I want it to be equal to 8 or more. So I would start off, and I'm giving myself that a little extra room to gain a little bit more probability. I'm starting off at a value that's less than 8. All right. So we go with 8.5. Let's see how the clock is going here. Period 6, 150. Okay. All right. So the next question, determine the probability that exactly 8 of the 25 water heaters will have at least 10 or last at least 10 years. All right. So I'm actually going to steal my number line. And just copy it again down here. No real good place to put it, so I'll just chuck it there. I might move it later, but I'm going to get rid of this box here. They're saying that we want exactly 8. So if I'm using the normal curve to do that, the only way I'm going to capture an 8, because we use norm CDF, that's always for an interval of values, so between this and that. So you'd say, okay, well, what numbers should I be between if I want to do this with a norm CDF? I'd have to be between some number less than 8 and some number greater than 8. All right, so a good place to stop here would be 7.5, going from 7.5 to 8.5. All right, so that gives me a nice little interval here that will capture the discrete value 8. All right, so again, I'm just going to use the more streamlined approach, norm CDF, going from 7.5 to 8.5 with a mean of 6.25 and a standard deviation of 2.165. So norm CDF range 7.5 to 8.5, 6.25, 2.165. All right, so it gives me an approximate value. I'm going to steal this. So about 0.133. All right, so this is an approximation. It's a question of an approximation of what? What was the correct probability? So I would check this. They didn't ask me to, but I will. Check it by using the binom PDF, right? A couple students in the other class asked a question that I got to imagine is on somebody's mind. How do you know it's binom PDF and not binom CDF? All right, binom PDF is for a single value. I look at it like particular value. All right, binom PDF is for a particular value. Binom CDF is for a collection of values. All right, so an interval. All right, so particular P, collection C. Any variation on that is probably okay. All right, so binomial PDF, we're looking at 8 with a number of trials 25, probability of success 0.25. And we get about 0.124. All right, so that 0.124 is the correct answer. That 0.133 is the approximation of that correct answer. All right, so there is a little variation. So you wouldn't expect it necessarily to land on precisely the same number. That can happen, but you wouldn't expect that. The problem with a question like this is that, well, really, I guess it's not a problem in your perspective, because on a test, I'd have to phrase it the way I did here, use a normal curve, right? And if I want you to use continuity correction, I have to say with continuity correction, so adding or subtracting 0.5 as needed. So it's pretty blatant, like you must use this procedure. The problem from your perspective is the 5 choices that you're given, because one of those 5 choices is going to be 0.124. All right, it's going to be the answer that you would get if you did not use normal approximation with continuity correction. So you just have to sort of train yourself to do it that way. All right, just kind of keep that in mind. When I see this, I do that. In terms of the value of a technique like this, it's really good for large sample sizes. The problem with that is this day and age, we have technology that is capable of handling large sample sizes. So it's kind of one of those topics that I don't want to say it's obsolete, but it's not as useful as maybe it was like 25 years ago when we were still using actually more than 25 years, like 30 years ago when we were still using tables to determine normal probabilities. Now we could do it all in a calculator. Now, if I had to type in a data set that consisted of more than 100 values, NumWorks isn't going to let me do that. It only goes up to 100 values unless they updated it. So maybe you can make a case that it's useful in that regard, but typically not really. All right, so it unfortunately might fall into the category of useful to know so that you can get questions right on an AP exam. Not in love with those types of topics, but it is what it is. I was originally going to assign a quizzes for this topic, but with the snow and potential for more snow on Friday, I'm not going to do that for this topic. But I am going to ask you to have a look at this second example for homework for tomorrow. And also, if you didn't get a chance to collect your daily data and you can do that over the next day that would be great.